SwayamPrabha. Digital India. Educated India.
Welcome back everybody. So we were discussing tensors in the last class, vector spaces and tensors, and where we stopped last time are this example of transformations, and we were discussing how if you have a column vector, then you can have this matrix, two-dimensional matrix consisting of 4 terms as a tensor that can operate on this column vector and give rise to another vector, right. So now these we had also discussed the definition of tensors, and this falls very much in line with that, because it is acting on a finite dimensional vector space, and then you have the vector space is also a real Euclidean space, right. So matrices such as these will represent tensors of some form. When we introduced transformations, we said that a transformation acts on a vector to give you another vector in the same space. I am not going to repeat that part again and again. I think from here onwards we will just take that as granted. But the idea is that you have a transformation which acts on a one vector and gives rise to another vector. Now you can generalize this idea, obviously, going even further, and you can define something, for example, as a 4 tensor. Okay. And 4 tensors, although we will not need it so much in this class, but I think it's just appropriate to quickly discuss this. A 4 tensor is a linear transformation, and we'll call it, let's say, C. Now we have already put 2 bars for a tensor, so we are just for 4 tensors. This is going to become a bit cumbersome. Let's put 4 bars, and it's called a 4 tensor if it acts upon an ordinary tensor, let's say some tensor A, and gives out as output another tensor. Obviously similar type of tensor, it cannot be a different type. So so here what we'll have is we'll write this as this, right. So C, let's say, acts upon A and gives rise to another tensor B. Now these are tensors we have already seen before, and this can also be called 2 tensors. Now 4 tensors are very important in the field of solid mechanics, continuum mechanics in general. We will not encounter them so much here, but it is just important to see how you can just take this idea forward and more forward. But in the experimental techniques that we are going to discuss, these tensors are going to be the important ones that we will encounter, and we will see why that is. Okay. So till now what we have been doing is we have been giving a very dry set of definitions for tensors, but it's important to understand why what some of these tensors can do and why they are needed. Okay. Now I want to add a page. Okay, this, wait a second. Yeah. Okay. So let's say I'll give you an example of an interesting tensor, and I want you to work out what this tensor actually does. I'll give you hints also. So sorry, my definition word is incorrect. It is an interesting transformation. So I'll give you this particular matrix. So this is a 3-dimensional matrix, consists, the first entry is plus cos theta, then sine theta plus sine theta, and then the next one is minus sine theta, and this is again plus cos theta, and we will populate almost everything else with a 0 except here, and I am going to ask you to see what this does. Now, this is a rotation matrix. So, I have already given you a very good hint as to what it will do, but I would want you to work this out for yourself. Maybe take a radius vector and operate, and so theta can be any value you want to choose. So, just put some value of theta and you will see that what this will end up doing is rotating that. So, I just want you to work this out. It is quite simple really, but something which is nicely illustrative still. Now, this rotation, the reason I discuss this is because you might have seen this before, but in mechanics the kind of tensors we are going to be dealing with, they are going to be slightly different, and there is a good reason why we deal with many of them. Now, in order to understand that, we have to understand the idea of deformation in a little bit more detail. So, we will look at deformations. Okay. So, we will have real bodies and we will have them deform. So, let us say we have a body like this, and I am just going to create some copies of this. Okay. So, I am going to create one more here, and now in this case what I will do is I will draw something slightly different. Okay. So, what I am trying to show here is you have some body which is shown here by this particular outline, right, and this outline you are seeing all over. Now, this is a body, let us say there were 2 points in it, let us say some point A and some point B, and let us say this is a vector connecting that. Now, this body has changed places and it is deformed, perhaps or perhaps not, but it looks exactly the same in this case. So, I am actually trying to show a rigid body movement here. So, this body has just gotten displaced in space without, so this is a rigid body motion. Sorry, this is okay, and this is a case where you actually the body is deforming. So, this is a case of deformation. Okay. So, here now these 2 points. So, in this particular case, in the former case, the vector A B is simply translated in space or rotated, but does not change as much. The relative positions do not change. Take any 2 points and they will not. But in this particular case where the body has deformed, you had so this is maybe A dash B dash. Okay. So, you had these 2 points, but now let us say the body has deformed and this new vector is now looking different, which is still connecting the same 2 points in the system, but the vectors are now very different. So, this body has undergone deformation, and now we have to, one of the ways in which we can understand deformation is by keeping track of these vectors that we had. So, what is a body? It is just a collection of many different points. So, we can draw all these vectors from, let us say, one point to other points in the body, and then we see how these radius vectors change, and that will give us some idea of the deformation. So, this is how we keep track of deformation. Okay, so we are going to look at deformation of a body. So, now the whole point is that what you have in solid in the field of solid or fluid mechanics is you have deformation of some sort, right? And the whole idea of the experimental technique is to keep track of this deformation. Now, just like we do for dynamics, what we will do is we will say that we have some coordinate system that is already set up. Now, you have this body that you had. I will just copy paste the photo from previous time, and this body is now undergoing some process and is now going to deform into a slightly different shape, right. So, this body has undergone some process, it has deformed. So, some deformation process is going on, and as a result the body is changing its size and shape. what is the causality for this is something that you might have to work out in your very specific case. So we are not here to specify why this body is deforming like that. The idea of the most experimental techniques is to keep track of this deformation and give you that quantitative information. And once you have that, then you can go back and address your query as to why that might be happening. But the idea of most experimental techniques stops at keeping doing a good bookkeeping of this deformation process. So how do you keep track? So we were just showing you last time that we have this radius vector that we had drawn between a point A and point B, and these are obviously arbitrary points, so you can choose whichever point. So we do that again here. Let's just say we have point A and point B, and we have a vector here, and then you have a new this is your A dash and B dash. So these are the same points, but in the deformed body. So now just like we do in dynamics, right, everything is relative. So motion of a body is relative. So you have to define the coordinate system, the inertial coordinate system with which you are going to measure, let's say, the velocity of a body, of a moving body. Similarly, in this particular case, you have to define the reference configuration of the body, because you know just the inertial reference frame is not enough. You also have to define the configuration of the body with which you want to compare the deformation, right. So you have to define something called as the reference configuration. So let's say this is the reference configuration. Okay. Now I have to be very careful here is that the choice is arbitrary. This choice of the exact reference configuration is up to the observer. So the choice is up to the observer as to what you denote as the point with which you are going to compare the rest of the process. For many different experiments, for example, if you were doing a tensile experiment where you had, let's say, a metal and then you are going to pull it at two ends, or then usually what people do is before they apply the force and before they start pulling, they will define that state as the reference state. But it is not necessary for you to do that. But here we assume that you know what the reference state is, and then what both the points A and B are moving with respect to each other. Now we are also going to do another thing. We are going to put a star mark and say we are going to study small deformations. What do I mean by small? Well, we'll see what I mean by small. We'll be able to apply some Taylor series expansions here. So let's say the point point A is displaced by, so A is displaced by u naught as a vector, and B is displaced by another vector u. And while I have drawn A and B here deliberately in an exaggerated form, actually A and B are neighboring points. The reason they are neighboring points is because I want to apply my tools of calculus, which we are all very familiar with and good at, and we will use that to understand the deformation. So there is going to be one more problem in this course, which is going to be with the letters we use to name our variables. When we see in fluid mechanics, the variable u is often reserved for velocity, but in solid mechanics, u is often used for displacement. So we obviously have, if you look into textbooks, you'll see that the variable u in fluid mechanics is almost always for velocity, and the variable u in solid mechanics textbooks is always for displacement. Here we are discussing both, so we have to be very careful in how we name our variables. So I'll just go ahead and use u here as as a variable for displacement, and then when it comes to velocities, I'll try to have ux, uy, uz to delineate that. But u, v, w will be variables to denote displacement. So my vector u is basically composed of 3 components u, v, w in the 3 coordinates in the 3 independent directions, and so I can relate my u to u naught by using the Taylor series expansion. And I have already said that the 2 points are neighboring points, so I can relate u and u naught through my Taylor series expansion, and so my vector u naught is nothing but the column vector u, v, w. Okay, so now I can go ahead and I can. Okay, one more thing was let's say this is this radius vector is r, and this radius vector is r dash. Okay, so r was the radius vector in the beginning, and then it became r dash. So that makes things consistent. And now the component of r in this case is rx plus del u by del y, ry plus del u by del z, rz. These come from Taylor series expansion, and similarly I do for all 3 cases. Sorry, not plus, not equal to plus sign. So this is again del v by del x into rx plus del v by del y by ry plus del v. I'm sorry, not w. Del v by del z by rz, and then w is, this is not, I have to put a not. So, so this is the relationship using Taylor series expansion. As A and B are neighboring points. Neighboring points means they are separated by a very small distance, dx, dy, dz. So that's why we are able to apply these. Right. So this okay. So my vector u naught is basically u naught, the v naught, w naught. Right. So I missed that naught here. So now if I want to understand how much has there been a change in my radius vector in the 2 cases, then I have to take these 2 radius vectors and do, so I have to take r dash minus r, right, and that essentially boils down to my u minus. So so now my, if I had to write the 3 components of this, z, then this is nothing but del u del x rx and you can you know how to, you can just copy paste. Actually, let me just do that. I can just copy paste myself here. I don't have to write it. So I'm just going to copy paste this portion. And then Okay, this plus is not required. Okay, so what we now is, so what we have basically been able to do with all this here is we have been able to relate this change in the radius vector, and there is some matrix that we have to populate here, and if we multiply it with the original radius vector, we are able to find the change, right. So, some matrix which is basically these terms that we have just written, so the derivative terms, and this now transformation allows me to connect the old radius vector to the radius vector in the reference configuration, right. I can write this down in a little bit more. I am going to use indical notation here to simplify things. You can just see that if you do not use indical notation, things just become very tedious here. So, just to simplify life for myself, I am just going to use the indical notation and say that my Ri is nothing but U I comma j to Rj, where this comma here comma denotes differentiation, as is with index notation, right. So, this index notation just helps us write this down in a more overall simplistic manner, and I can and now, so this U I comma j, we already know what this is because we already worked it out. It is nothing but this particular matrix. Right. So, if I had to okay. This matrix, which is I think you all understand is a tensor, is also called the displacement gradient tensor. Okay. And you can see why it is a tensor. It is acting on one radius vector to give you another vector, which allows you to keep track of the changes that are happening at the deformation. Now, it is usual for us to write down this particular tensor, the displacement gradient tensor, as a sum of two other tensors, which I will call Eij plus omega ij, where this is also called the strain tensor, and this is also called the rotation tensor. Where Eij is defined as half of U I comma j plus U j comma I. So, the order is reversed, and omega ij is nothing but U I comma j minus U j comma I. And actually, one of these matrices is a symmetric matrix, the other is an antisymmetric matrix. I urge you to read up on that. Now, in this particular course, we cannot go, there is a fair bit of mathematics that is required in some sense in order to appreciate the experimental techniques in full detail, but this is not a course on the mathematical preliminaries required for that. We are just going to try and give you a feel of what are the important things, so that you can go ahead and read them by yourself, and make sure that you are familiar with the required amount of mathematics, because we are going to need that need that to understand the output of the experimental techniques. So, this is something that you should just make sure you do. I also switched off to an indical notation right here just to make my life easy in writing down all those terms. So, so we had set out to understand deformation and how deformation is relevant in the sense of tensors and and here we have two tensors that are very important, which we saw, the strain tensor and the rotation tensor. Now, in fluid mechanics, you do not see the strain tensor so much. In fact, what you do see is the strain rate tensor, which is nothing but the time rate of change. So basically, this is the strain tensor is something that you will see in solid mechanics quite a bit. Because that's what usually is the required output. You want the strains to be known at the at a given location. Whereas in fluid mechanics, what we are looking at are the strain rate. So we are usually not dealing with the displacements themselves, but we are dealing with velocities. So in that case, the important tensor is the time rate of change of that tensor. So it's Eij with the time derivative of that. So here you can these do not, u does not remain just the displacement term, but becomes the velocity term. Sorry, the time derivative term also comes in. So what we'll do is today we will stop here. Next time I will try to give you a little bit more of the geometric interpretation of these deformations and these tensors, and from the geometric deformations that will help you get a better appreciation of why this is needed, especially in a course that is designed to help you do experiments and analyze experimental data. So it will help you with that, and then from there on we will introduce ourselves a little bit more to the optics that are usually going to be very relevant to some of the experimental techniques before we fully start on to understanding some of the experimental techniques such as PIV. So we'll stop here today, and thank you very much.